In our last lecture, we derived system equations for this mechanical system. We had three C elements in it, contributing respective generalized displacements. And we had one I element, which was contributing a generalized momentum. So we proceeded with the two steps, step 1 and step 2, and algorithmically we proceeded to obtain the system equations which have been outlined here, Q1 dot, Q2 dot, Q3 dot, P4 dot. So these are actually in the state space form, which is a first order state space form. The left hand side is the derivative of the states. It tells you how the rate at which these states are changing with respect to time. And on the right hand side, you have states and parameters. Let's take an example today of an electromechanical system, the bond graph for which we have already constructed in our previous lecture. So here we have the electrical system and the mechanical system and the electromechanical connection between the two. So here there is the source of effort, which provides the potential difference Vt. On the electrical side, you have the armature inductance, La, represented by this I element, and you have the armature resistance given by this Ra. And you have the electromechanical action due to the motor, due to the motoring action, due to the electrical side, resulting in the development of a torque, and that moves, that drives the mechanical side. So the rotor starts to rotate with an angular velocity of omega. J is the moment of inertia associated with it. And we have also considered joint bearings here with RP as the damping associated with this. We can see that the relationship for the forward side is that torque on the mechanical side is related to the current using this relation. Torque is equal to mu into Ia. And because the rotor rotates, there is a back EMF which is generated, and that back EMF is equal to mu into omega. Okay. Now let us see how to derive system equations for this electromechanical system. It's a very common, very useful electromechanical system. Now, let us start with our procedure. So this is the physical system. This is its bond graph model. And we start with the first step of the algorithm. What do the elements give to the system? See, we have discussed earlier that it is a question relating to the output. Okay, what is the output of the elements? So we start with the first element. We start with sources always. So we'll start with the first element, that is, what does this source give to this? It gives effort 3, and effort 3 is equal to V of T. Okay. So we know effort 3. The next is, what does this I element give to this system? It gives flow 1. Flow 1 is the electrical momentum associated with this I, that is a flux linkage, divided by La, which is the inductance of this winding, armature winding. The next question is, what does this I element provide to this? It gives flow 2. So here also you can write this as flow 2 is equal to P2 by J. So for these elements, the questions were simple, and on the right hand side, you had in terms of states and parameters. We still have two elements, RA and RB, yet to which these questions have to be asked. So let's start with RA, and we see that if we proceed like this, yeah. So the first is, what does this R element give to this system? Effort or flow? It gives effort to this system. This effort can be written, if it is a linear armature resistance, it can be written as RA multiplied by the flow through this armature, that is the current. So RA into flow 4, and flow 4 is not known, but we can determine it from here. Flow 4 is coming from this one junction. It is being brought in by this bond number 1. So flow 4 is the same as flow 1 because this one junction is a common flow junction. So flow 4 is the same as flow 1, and flow 1 we have already determined as P1 upon LA. So we can write this as RA into P1 upon LA. So this is our first step. The second is, yeah. So we asked this question for this R element. Now, what is the question for? We have to ask the same question to this R element. What does it give to the system? You can see it gives effort 7. So now we proceed here. Effort 7, it can be written as R B multiplied by flow 7, assuming it to be a linear damper. Okay. The bearing resistance is assumed more like a linear damper. In that case, it can be assumed as effort 7 equal to RB into flow 7. Now, what is flow 7? Flow 7 is coming from this one junction. It's a common flow junction. The bond which brings it in is flow 2. So flow 7 is the same as flow 2. And that is clear here. Flow 7 is the same as flow 2. So you can write flow 2 was already worked out earlier as P2 by J. So effort 7 can be written as RB into P2 by J. So you have the answers to the first question asked for all the elements. Now we proceed to the next step of the algorithm. What does the system give to elements with integral causality? So what does the system? There are only two integrally causal elements here, these two I elements. Let's start. They are each of them are contributing their respective states. We have the state contributed by this one, which is the flux linkage P1, generalized momentum associated with this. We also have the angular momentum, that is P2, that is the angular momentum of this rotor, which is moving with angular velocity omega. It is given by this variable P2. So we start with the second question. In the second question, yeah. So we ask this question, what does the system give to this element, effort or flow? You can see from the causal structure, it is giving effort 1 to this I element. So effort 1 can be written as, in terms of its state, it can be written as the derivative, time derivative of P1. So effort 1 is equal to P1 dot. And you can see that P1 dot, that is this effort 1, is actually effort 3 minus effort 4 minus effort 5. Okay, effort 3 minus effort 4 minus effort 5. Effort 3 has been worked out here. It's V of T. Effort 4 is also available here. And effort 5. What is effort 5? Effort 5 is mu times flow 6 because it's a gyrator relation. So effort 5 is mu times flow 6. Okay. What is flow 6? Flow 6 is coming from this one junction. It is being brought in by this bond. Flow 6 is the same as flow 2 because this one junction is a common flow junction. So flow 6 is the same as flow 2. And flow 2 is already known to us as P2 by J. So if you substitute these uh, efforts, the variables, in this effort 3 is VT that is placed here, minus effort 4, which is RA by LA into P1, RA by LA into P1, minus effort 5, which is minus mu into P2 by J. Okay. Effort 5 is the same as mu into flow 6, and flow 6 is the same as flow 2. So we have got this expression for the first, this is the first system equation for this system. You can see the left hand side is derivative of the electrical momentum or the flux linkage, and the right hand side is in terms of states and parameters. Now we ask the question to this RL, to this I element. What does the system give to this I element? Effort of flow. You can see that it gives so you can see that it provides flow to the system. I'm sorry, it gives effort to this I element. So this effort to this I element is P2 dot in terms of its state. It is the derivative of this rate of change of this momentum, and that is mu multiplied by P1 upon it. We'll come to this. So it is P2 dot. And what is P2 dot? It's coming from this one junction, effort 6 minus effort 7. Okay. And we know effort 6 is mu times flow 5 from the gyrator relation. So effort 6 can be written as mu times flow 5. Flow 5 we already know, and flow 5 is the same as flow 1. So the right hand side gets worked out. This is mu upon LA into P1 minus RB by J into P2. Okay, when you substitute the variables and parameters. So you have the second equation for this system, and you can see that there are only two equations, system equations possible for this system, because there are only two state variables associated with it. Okay. And left hand side is in terms of the rate of change of these states, and the right hand side is in terms of states and parameters. Let us now cast these in terms of, we could write them in a form which is a matrix form. So I'll be showing you this matrix form. We take the derivative of these states on the left hand side. Okay, we arrange it in a vector like this. So this is the derivative of the state vector. Okay. And this is equal to this matrix. We'll call it as the matrix A operating on the state vector. Okay. Plus another matrix B operating on the vector of inputs. Now we have only one input in this, which is this source of effort, Vt. So let's now write this first equation in terms of this matrix form. We have P1 dot equal to V of t, that is 1 into V of t, minus RA by LA into P1, minus RA by LA into P1, minus mu upon J into P2, minus mu upon J into P2. So you see the first row of this matrix has been determined. The second row of this matrix can be determined from the second equation, that is P2 dot equal to mu upon LA into P1, mu upon LA into P1, minus RB by J into P2, minus RB by J into P2. Okay. And here you will have 1, 0 multiplied by V of t. The input vector is only 1 by 1 over here. Now you can see that the state vector is shown here as x of t, x vector. Its derivative is available on the left hand side as the time derivative of the state vector. This matrix here is the state matrix. Okay. And this is the matrix A. And it is operating on the state vector. And here you get this matrix B, which is operating on the input vector. Okay, so this is the form in which you can always get equations for linear systems. In fact, these need not be linear also. You can, if they can be expressed in a form like this, you can conveniently obtain this. This is the form which most electrical engineers and control engineers use when they apply linear control theory. So that's the reason we have cast it in this particular form. It's not necessary. Let's proceed to, yeah, so this is what we have done over here. Now we will, usually when we have a problem like this, we are interested in measuring the angular position of this shaft. Okay, angular position of this rotor shaft is of interest to us. We would like to measure it. So how will you obtain it from this bond graph? You can see from the previous bond graph, there's only this an element over here which is different over here in this. Everything else remains the same. We just added this bond and placed a C element here. But this bond, we took care to see that it is a signal bond. So we put a full arrow here. So it does not deal with two variables, but with only one variable. That means the information which it is carrying. It's just information, no power. Okay. So this is also called activation, activated bond 8. This is the number of this bond. So it's the activated bond. What we are doing here, what it is doing is it is just pulling out the flow, the angular velocity, and telling it to the C element. The C element is just going to integrate that angular velocity and determine the angular position, which is of interest to us. So it's just performing an integration task. But because it is a sensor, it is not going to alter the dynamics of the system. So it's not going to apply an effort back on the on this system. So effort 8 is actually 0. Effort is not considered. Okay, effort is considered as 0. So actually it is just a signal bond. A signal bond does not carry power. Okay, for the transmission of power you require two signal bonds, both directed in opposite directions. So you can see that Q8 Q8 dot is actually the angular velocity. So Q8 is actually the angular position, and it can change with respect to time. So this part which we have added subsequently, So this is our these are our initial system equations. This part which we added, it's just for us to perform this measurement of the angular position. So we write this so that we are able to obtain the angular position from this equation. Okay.